So once again, give it up to Chinmay, CTO of Subneuro.
Hi folks, welcome to my talk at GeekCamp on the software best practices in the hardware world. A quick introduction about myself. I'm an engineer. I work at Subneuro, where we make underwater Wi-Fi effectively. I also run a monthly meetup, a hardware meetup called Hackware. It's kind of on a hiatus-ish now, but hopefully we'll be back soon. And I've been working at this intersection of hardware and software for about 15 odd years. And one of the things that I've noticed over all the time I've worked here is stuff that we consider normal and best practices in software world are not at all used in the hardware world. We'll go into some of these things and what they are, but before that I want to do a quick definition because this gets confused quite a bit and people don't know what they're talking about. Hardware is a very generic term. I'm using this a lot in this talk, but what I mean is sort of mechanical engineering, mechanical development, and electronics engineering and development for making standard products. So this could be watches kind of stuff, or mobile phones, whatever, things that you use on a daily basis. Since I've did definitions, I would quickly like to get a poll. How many people here only do software stuff? Quick raise of hands. No, that's not true. I love all of them. Software and hardware? All right, we got a bunch of them. Cool. Hardware only, anyone? Anyone? No, I don't think those people exist anymore. But yeah, I guess everybody does some sort of software here and there. And that means most of us would be very comfortable with some of the best practices I'm going to be talking about. So when I was working at Subneuro, one of the things I sort of tried to think about and do was to see if some of these best practices we use commonly in the software world can be applied, and not anyhowly applied, but can be effectively and practically applied so that people want to use them and we get the benefits out of them. So just to give a concrete example of what we're talking about, I'm going to be taking an example of one of the devices that we make at Subneuro. So this is one of our underwater Wi-Fi devices. And to make something like this, you would need a bunch of mechanical drawings and assembly drawings. You would need electronic schematics. You need layouts of them. You need the bill of materials of the electronics. And you need code. And a bunch of these are documents. And the documents would need versioning and version control. And then once you have and build all the components, you got to put them together. You got to test them. And then you got to integrate them and sort of put everything together and test it again. And coming from a software world, these words look very familiar, right? I mean, version control, versioning, integration, testing, this is stuff that we do on a regular basis. So can stuff that we have learned in a software world be applied to hardware development and engineering? So let's take them one by one. Let's start with versioning. Unfortunately, there's no standard versioning scheme in the hardware world. I have some examples of the kind of documents I have seen in the repository I have. Stuff that you've seen as horrors of, underscore latest, underscore latest is very common. People just make up their own versioning schemes, and then you get this really awkward problem with saying, the mechanical assembly version 4 Mark II, is it compatible with revision 101A of the PCB? And there is no way you can figure this out. Of course, the software world, we have figured out this with semantic versioning. It is kind of a standard. It is widely adopted, though. And it's got this idea of having a major version, a minor version, and patch version, and a set of rules that explain to you when you should use this. What we did at Subneuro, we sort of created our own variant of this, in a way. This is sort of how we define major, minor, and patch. And what we wanted to do was to basically be able to understand what changed between two versions at a glance without needing to go through all the change logs and figure out exactly what it is. So this mechanism helped us use SemVer, and it's been working quite all right. The next one I'm going to talk about is version control. This is a hairy one. So all documents need version control, and of course Git is the most favoritist of all of things available these days. Unfortunately, a lot of electronics and mechanical CAD tools tend to have proprietary binary file formats, and that just breaks down with Git. You get stuff like this. Somebody changed a file, added 512 bytes, don't know what happened. Even some CAD programs that use text files, you get a diff like this, which is great. It's kind of hard to see, but it's a bunch of numbers that changed, and nobody has any clue what happened. And the reason for this is, while Git itself can deal with this with binary files, no problems, or even text files like this. None of the user interfaces built on top are designed to be able to make sense of what happened between these two. But still, using Git gives us a bunch of good things. It gives us tags and commits, which work regardless, so you can still go back to a release and figure out what happened. It gives us branches and pull requests, which are still useful. But the most interesting thing, and this is something I think going forward we might get useful, is to have, in Git parlance, it's called porcelain. It's basically a user interface or a user-facing side of Git that could deal with some of these things. So there's a company called Allspice that's using some of these things to basically show a nice view. So this is how electronic schematics look like. So it would be able to do diffs on these things to say, this changed or that changed. And this is nothing fancy except a plugin for Git, right? So once we have a good ecosystem of these things, and hopefully they're open source and non-proprietary, currently this is completely proprietary, I think this is something that would totally be usable in a electronics design kind of a workflow. So currently we're still using with the commits and tags and the PRs and the branches, but I think with custom porcelain and GUIs built on this, I think some of this stuff could be easily translatable to the hardware development world. The last one is continuous integration and continuous deployment. This is the ultimate goal in software development best practices, right? People want to be able to deploy things. It's impossible to continuously deploy things in hardware, right? You can't be shipping people new Apple Watches every time there's a new release. So that's not happening. But even continuous integration is hard. And one of the main reasons is the time between designing a piece of hardware, so making a schematic, and then getting a working circuit board in your hand usually tends to be between days to weeks. So you're not going to be able to say, I change something, I ship it out, I get something back and I test it. So that repetition cycle is very, very slow. The other problem is that testing hardware requires custom hardware and custom equipment. A lot of times these equipments are expensive, so usually you might only have one. A lot of times you might even need to make custom equipment just to test your hardware. And most of the time, these equipments don't have nice APIs. So they're usually using some ancient interfaces, or even if they have some. So there's no way for you to be able to control them and say, do this, do that, and then get stuff out. This is even harder on the mechanical side of things because, for example, things like multimeters to check, micrometers to check how long or wide something is. That's very, very hard to automate those things. So this stuff gets very hard. What we did find out is if you restrict your usage to just testing the software on the hardware, you can get quite a bit of the benefits of CI, but it actually can work. The awkward bit is you need to test the software on the hardware you're making. So in our use case, we have to test the software to work on the piece of hardware that I was showing you earlier, or some subsystem of it. What we figured out that we could do, and this is something that we have been doing quite a bit, is to have the hardware that we're testing on here, to have some kind of a host machine, and a test input generator and test output generator. And this would basically allow us to test the hardware through a host machine. So the host machine runs your GitHub CI runner or whatever your continuous integration host client is, compiles the software, programs the device under test, and then gives it the right input, and then records the output, and then checks whether that conforms with the test spec that we have. This has kind of worked well for us. It is a custom part of, or a subsection of CI that we can do, but it at least allows us to test a significant part of our software chain on the actual devices they're going to be running. The nice thing we figured out was we could actually remove one of the test devices, so you could just use another of the Wi-Fi, underwater Wi-Fi devices, and then just use it as both the generator and the recorder. It's just the way our devices work. It allows us to do this and just makes it a little bit easier to do. So this is a test of setup. This is a photo of a setup that we had last week. So this is one of the devices that's being tested. This is sort of the golden device, and then there's a host computer set up somewhere up there out of the picture. And then we're basically driving this guy, getting this guy to send the right signals to this guy, and then this guy outputs the right signals back to here, and then we record it back on this, and then verify if everything is working fine. awkward but doable, and allows us to sort of do some amount of continuous software testing on our devices. So back to the question I asked at the beginning, can software best practices be applied to hardware development? Hard, but not impossible. I think if you get creative, you can extract the essence of the best practice and apply it in context of the hardware. I think there's a lot of scope for doing these things. The velocity that software teams usually can manage to get is much, much higher than hardware teams. And I think using some of these best practices in hardware development, we can try to close the gap and develop hardware at a much, much faster pace than traditionally what's being done. So that's all I have for the talk. A quick plug. If you like to work on hard problems, if you think underwater wireless is interesting, we're hiring, so come talk to me after the talk, and I'll happily tell you about what we do at SubNeuro. So that's all. Questions?
Thank you so much. Sam, do you want to lead the Q&A?
Yeah, sure. Let me open up the Q&A real quick. But I guess most of the folks here are more like software based on your survey, so I'm not sure.
Yeah, I have a question.
Yes.
So nice to meet you, Chinmay. So one question is, I think you have used LT-Spice, right? So it only went for Allspice or like.
So Allspice is not. It's a horrible name. It's a startup that does basically Git for electronic schematics.
Okay.
So it's not related to LT-Spice, which so Spice is an electronics emulation simulation program. They use the name, but it's unrelated. Yeah.
Okay.
I've not actually used Allspice that much, but I think they are doing the right thing, and I think that's the direction we need to go to be able to use some of these tools and techniques in the hardware world.
So I know about LT-Spice, but Allspice is very new to me.
It's a startup based in San Francisco. Yeah.
Thank you. Yeah.
Yeah, I don't see many questions. If you have 5 minutes, you want to do a quick plug for. Oh.
One question.
Yes.
You mentioned you had to test it on the device.
Yes.
Is there any way to simulate that?
Yes, and I think I kind of wanted to talk about that. I didn't get much time to talk about that since exactly what I wanted to talk about. I don't have internet connection, but I think emulation is another big part of the story that I didn't get a chance to cover. I think that's the other bit where you can get some really, really interesting things going. I think it's a very nascent area though. I think good emulation is still very hard, and if you want to look at the whole product, you need to start emulating the electronics, the software, the mechanical side of things if need to be, and that gets very, very complex. But I think if we push down that route, we should be able to get a lot more in that direction. I think that's a great direction to definitely go in.
So there's no Chrome dev tools for SubNeuro?
Well, we do use Chrome dev tools. Let me see if I can bring up Walkui.
I'm actually very curious. Like, what does it work? Because it's like underwater Wi-Fi, is it?
You want to talk about that? Yeah.
Yeah, I want to talk about that.
Sure.
Underwater
2
Wi-Fi.
minutes.
It's fascinating.
We have 2 minutes to plug. 2 minutes to plug.
All
You
right.
have 2 minutes.
till I pull up Walkui. Underwater Wi-Fi, so we use acoustic signals. So we use effectively sounds, similar stuff that dolphins use, except we send bits and bytes instead of sending, dolphin talk.
What is like the practical applications of this?
Underwater sensors, underwater robots.
So is it like sonar? Sorry, I'm just asking a lot of questions.
It is like sonar, but traditionally sonar was used for imaging,
Right.
or similar kind of stuff. But this is more used for comms. So
Like
sending,
Wi-Fi.
yeah, sending
But
sending
like
sending
Right,
bits and
right,
bytes.
right.
Quick one. So Sam talked about somebody talked about Walkui. So this is a super cool emulator. If anybody is into hardware, this is actually a freaking awesome thing. So this actually emulates the entire hardware setup here, including all the buttons and the buzzers and the LEDs and everything in software in your browser. And you can write code which I think goes to the server, gets compiled into the actual binary of the processor that is running on this emulator. And in the processor's emulator runs that binary code and then emulates everything on this thing. It is.
You can write your own firmware and
Yeah.
run it.
So yeah, you can. I'm not sure if you can just hear it. Yeah, something's happening. All right. Anyway, do play with it if you're interested in hardware kind of stuff. I think this is kind of toyish, but I think from a more industrial perspective, going down this route is exactly where we need to go.
So I mean, like, there's also like games you can play. Shanghai I/O is very fun.
It is. Yeah.
Wait, I thought it was
Shenzhen
Shenzhen.
IO.
Is it
Shenzhen I/O, sorry, Shenzhen
But that's,
I/O.
Shanghai doesn't have the
that's
Shanghai
more.
IO.
That's more. I'm not sure if this works, but that's more. That's more fun stuff.
It's a fun game. So it's a game
It
where
is.
you pretend that you are a Shenzhen engineer trying to steal people's code. That's it. Steal people's technology. Yeah.
All right.
I have a friend who was playing it, so I was fascinated. That's why I play with it.
Cool.
Okay, so we are gonna move on. Thank you so much for your another round of applause.